Start off. I'm going to read the answers and then we'll go over the ones we need to go over. Okay? Okay, so number 1A. It's random. We've got $2,674.38. Good? Okay, part B. 26. Is this right? Oh, the interest rate went down. Okay, I was like, because the amount went down. 2654.49. Daily, we're looking at 2622.92. And then part D, you have to use your PERT formula, which gives me 2570.99.
Why did they pick the same letter for two different constants or whatever?
The same letter for two different
constants. Lowercase e is Euler's number, and then the capital E is scientific notation.
Yeah. Yeah. I don't know why they did. It is important to it is important to pay attention to your capitalization. Okay, let's see. 2A, we've got P equals 500 times 1 plus 0.06 divided by 12 to the power of 12t. And they were just asking for the formula or the equation. Okay? Because it's compounded monthly. Okay, part B. Okay, how much money will Martha have in her account 1 year from now if she never withdraws any money and reinvests her interest? So I heard you discussing this. If she's reinvesting the interest, that is compounding. So we're just using this compound interest formula that we wrote just above. So we'd have $530.84. Skipping part C. Effective interest base. Well, I'll just quickly explain it. Okay. So effective interest means you're going back to the simple interest. So for instance, in this example above, right, we have $530.84 at the end of 1 year, which means you have $30.84 at the end of that 1 year. So if I made, right, interest equals PRT. If I made $30.84, what's the interest rate that I made? So I started out with $500 R, and this was over 1 year. So we'd have 30.84 divided by 500. Is that right? Okay, so what does that come out to?
6.17%.
Okay, so 6.17%. Okay, so the effective interest rate is 6.17%. Because when we talk about effective interest rate, we're talking about simple interest. Okay? So we calculated a compound interest of 6% for that 1 year, which is the equivalent of 6.17% if you did simple interest. Okay? That's what effective interest means. Okay. Yeah, probably. I think that's a pretty straightforward concept. Yeah. We skipped number 3. Number 4. I told you to skip it because I hadn't taught you effective interest rate, but let's look at it now. An initial investment of $700 is worth $725 a year later. So how much interest did I earn? $25. What is the effective annual yield of this account? Okay. This one, we've got to figure out the effective interest and then figure out how much we would make each year. I'm not going to ask you to do that, so we're going to skip that one. Okay.
Doesn't the amount change each year that you get, though? Is it not compound interest?
When we talk about effective, it's not going to be compound, correct? Yeah. Okay. Number 5. Let's see. For 1 year, $1,419.07. For 2 years, $2,013.75. We good? Okay. The last one. Okay, this one you had to think a little bit. So we're at $25,000. It depreciates at a rate of 12%, right? So our compound interest formula, if you remember when we first started talking about all of this, this is actually an exponential formula. And remember in the beginning, I said I think I was relating it to SAT questions. When this number is greater than 1, that means it's growing. If it's less than 1, it's decaying. Well, when we talk about depreciate, we are talking about decaying. So if I start with $25,000 and it's decaying 12% per year, or depreciating 12% per year, then that means it's growing 0.88%, right? So this would be a growth function. This would be a decay function. Right. So we're going to do 1 minus 0.12, which gives me 0.88, and this is just to power 5 years. Okay, a decay function we subtract, so it should be less than 1 if it's a decay function. It's greater than 1 if it is a growth function. So when I calculate this, I get $13,193.30. That's how much my $25,000 car is worth at the end of the 5 years, if it is depreciating at 12% per year.
How did you get the 0.88 again?
1 minus 0.12. Okay, because this is my decay function here, and this is my growth right here. Okay, so relating this back to y equals a times b to the x, right? If b is greater than 1, it's a growth function. If b is less than 1, it's a decay function. And when we look at this, here's my a, and here's my b. Okay, that makes sense to everybody? Okay. I feel like we have no time today. What in the world happened to our time? The video is too long. It's okay, though. It's enjoyable. Okay.
Well, yours. Mine was like,
Mine
yours
was
was
like,
in a minute second.
Okay.
mine was
So-
2 minutes and 15 seconds.
So
We were
what
not-
we're looking at with all this, guys, we're looking at exponential growth and decay, but applications of exponential growth and decay. All of this compound interest stuff, this was all an application of an exponential growth function. That last example is exponential decay function, all right? So another place that we can use the exponential growth functions is when we talk about population growth. So here are some examples of that.
Population control.
Very applicable for if you're living in this area that has like this incredible population growth, right? This part of Florida in general, the population growth is just like going through the roof. Okay. Notice the formula, because population, right? It is a compound growth. It's an exponential growth, but it is continuous. You know, that's why we use population as an example. We don't grow in population and then stop, and then start, and then stop. We don't do that. Population is continually growing or decaying, and in Florida, it's it's growing. I don't think in my entire life I've ever seen the population of Florida go down. Notice the formula, it's the same formula. NERT instead of PERT, it's the same formula, okay? The N stands for the initial amount, right? So it's the same thing, but we're using E because it's continuous. Okay, so we're going to just quickly go through this together. Population in Fred, yes?
What's the little zero next to it?
Lindsay, what's the little zero next to the E mean, next to the N mean? Because I'm pretty sure you asked that same question, didn't you?
Yeah.
What's it mean?
The base amount.
It's the base amount, the initial amount. And that is the case in any formula. You'll see that in science a lot, right? When you have a sub-zero like that, that's called sub-zero, that means initial amount, as opposed to something that looks like this with like a sub-F, that will be final amount. Sometimes you'll see it with an I, but more often you'll see it with a zero, meaning the initial amount, starting amount, okay? All right, population in Fredericksburg, Virginia was approximately 19,360 in 2000, has been continuously growing at a rate of 2.9% each year. Predict the population in 2013, okay? So same thing, population in 2013, right? It's going to be equal to our initial population, 19,360, times E. What's the R? 0.029. And what's T in this case? 13, right. Okay.
This way.
Yes.
When we're doing like population, there can't be like a decimal. Can't be like
Very good observation. Yeah, we're dealing with population, so it's not going to be any decimal. So we have to round this. So I'm going to round it. We're going to round it below, right? So 225. We're not even going to round it according to the rounding rules. We always round it down. Because if you have 0.75, we can't round that up to a whole person. Okay. Okay, good with that one? These are easy, aren't they? Once you understand what you're being asked. Okay, using the same information, what's the population of Fredericksburg, or what was the population of Fredericksburg in 1960? Oh, 1960, how would we do that? Yes.
Put a negative in front of the percentage.
Okay, so let's try that. 19,360, right? And you're saying do negative 0.029. And let's see, how many years would that be? 40? Let's see if it works. Okay. I'm actually putting the negative on the 40, but because it's multiplication, it doesn't matter. So we've got 6,069. Okay. I want to go the other direction and just check it. See if it makes sense. Okay. So let's see. If I start off with 6,069.
when I try to plug that in this thing here.
Okay, I'll come help you in a minute. When I start with 6,069, 2.9% interest for 40 years, do I end up with 19,360? Let's check it out. It's going to be a little off because of the rounding, right? Okay, so I ended up with 19,359.7. So my number is good. Okay? Did you get it figured out, Jack?
So the photo.
Okay. Anybody else having trouble with the calculator? Okay. Number 3, Texas is growing at a rate of 3.9% per year. The population 2010. Okay, same problem, right? Go ahead and do that. Did you guys get a big number? Okay, just checking. Oops. Okay, so I got 960,095 people. Okay. Okay, see if you can do the last one. This one is a declining rate because it's different than the declining rate that we did on the other worksheet. Okay, the other worksheet, when we looked at the declining rate, we were subtracting that rate from 1, but this is not a regular compound interest. This is continuous compounding. So it's a different formula. So what would I use as my rate? Negative. Yeah, make the rate negative. Good.
Make the rate
Wait, is it just 0.02, not 0.002? No, wait, yes, you're right, because it's 0.02%. It's 0.2%.
Right. 0.02 would be 2%.
I think I.
Just divide it by 100. 0.2 divided by 100. So 39.50. I lost you?
No, like you said, like it's not the same thing as the last one, but
Because the last one, it was that kind of formula, and we just changed that to a negative. This one is the E.
no, I was talking about like up there, number 2.
Yeah, it's the same thing.
Yeah, that's not,
I wasn't referring to
No,
that.
She was referring to this worksheet, not number 2. It's the same as number 2 on this worksheet. She was saying it wasn't the same as the last worksheet.
Right.
Even with. Oh.
So we have one that's in the-
Okay, so I get an error. Hold on a minute. Okay, here we go. 3,043,132.
wait,
Okay. Yes.
So the last decimal for me was a 9. Would you round or would you truncate?
Truncate. Yeah, because we can't round the person up. Yes. Basic question? Oh, you got it, Lindsay? Okay. Half-life. Half-life.
It should be that. You put minus in there, so that
I don't think we're going to learn half-life in chemistry.
Well, that's okay. We'll learn it here. Okay, so let's just start off by discussing basically what half-life is, right? So I think you guys told me yesterday, what is half-life? Half-life is the amount of time it takes for the substance to decay to half of its life. Okay? It is exponential because how can I explain this? So if I have a substance that's decaying at a rate, let's say that it takes 10 days to decay where it has half of its original substance. Let's say I had 100 grams. In 10 days, I have 50 grams, right? So in 10 more days, how much will I have then? 25 grams, right? So it's how much it's taken to decay to half of its amount. That's exponential. In the first 10 days, I lost 50 grams. In the next 10 days, I lost 25 grams. Right now, I'm down to 25. In the next 10 days, what am I down to? Okay. All right. So I can see on your faces, some of you are getting it, some of you are not. Right. I start off with 100 grams. Right. In 10 days, I've decayed to 50 grams. Right. Which means I lost half of it. Right. In another 10 days, I lose half of it. So I'm down to 25 grams. In another 10 days, I lose half of it. I'm down to 12.5. In another 10 days, I'm down to half of that, which is 6.25. In another 10 days, I'm down to half of that, which is 3.125. Right? In another 10 days, I'm down to half of that, which is 1.5 something, right? Whatever. Okay. Will I ever have zero substance? No. It's going to continue to get half. So this is going to be a decay function. If I were graphing it, it would look like this. Okay. 1.625? 5625. Okay. And then half of that, what's half of that? 0.7. Okay. And then half of that, 0.39. Okay. And then we're going to keep going and keep going and keep going. Right. This is less than 2. Yeah.
Well, surely eventually you'll have zero because once you get down to one atom left, you can't have half of an atom. So wouldn't it just decay to
That wouldn't be zero. No. No, but I don't know this. I don't know the chemistry enough to know what actually happens. But it's not going to just disappear.
Sure. Well, no, it decays into a different atom, but the atoms don't disappear when they decay. They turn into different elements, right?
Okay. Yeah, I'm saying that sounds plausible, but that's not disappearing. It's
But
not
yeah,
zero.
But like once you have like one, let's say it was carbon 14.
So first off, this is not a number of atoms. This is a mass. Right? So yeah, if you take the molar mass of the particular substance. So that's a good question for Mr. Roberts, because at that point I know, okay, so we get a certain molar mass of the substance.
Because surely because the reason why we can't study higher up elements is because they decay too fast for us to study them.
Mm-hmm.
So, but surely if there's always some amount of it left, we would be able to study it. Their half-life is too short.
So you're saying we get to a point where, because the quantity of the element or the mass remaining is so small that it loses the characteristics of that substance.
I think that's what I'm saying.
Okay. Good, Mr. Roberts questions. Okay. Excellent. Okay, so everyone understands what half-life is now, right? Okay. This is actually our formula for half-life. Now, you will see this in different forms sometimes. I find this to be the easiest form to work with. Okay. And what does N sub 0 stand for? The initial amount, right. So that would be our initial amount. Okay. 1/2 is our base. That's why I like this particular formula. Okay. And then the exponent is the time divided by whatever the normal half-life is. So let's look at an example. Carbon 14, okay, we always hear about carbon 14 dating and all that stuff, right? Carbon 14 is a radioactive isotope. Okay, how many grams, what's the mass of carbon normally? 12, right? So carbon 14 is going to have, so it's 12, so how many protons and neutrons does carbon have? 6?
Cool.
Look it up on your calculator.
Oh yeah, you gotta like a table or something. Like,
Let me see here. If you go to your apps, you have periodic. You can look that up, and you can look up your carbon 14 list. Carbon. Here we go. Okay.
Six protons and 8 neutrons.
Okay, and it has a mass of 12.
Where a lot of users calculators during.
You didn't know you had that? Yeah. So I'm looking at carbon 14. Okay. All right, tells me atomic number is 6. It's got my symbol. My mass is 12.0096. 6 protons, 6 neutrons. So an isotope, have you learned this in chemistry? An isotope means that it has a different number of protons and neutrons, right? Which is why it has a different mass. So carbon 14 has a mass of 14 instead of 12. Okay. It has a half-life. It has a half-life of about 5,730 years. So that means when I look at the carbon 14, which normally has a mass of 14 grams per mole, right? Am I saying that correctly? I don't want to get myself in trouble in chemistry, but 14 grams per mole, right? In 5,730 years, it will have 7 grams per mole, okay? So, while a plant or animal is alive, the amount of carbon 14 present is constant. Okay, you've heard that term, we are a carbon-based life form, right? While we're alive, the amount of carbon does not change. When the plant or animal dies, the amount of carbon 14 begins to decay. I think, to me, this is just like a fascinating and cool application of math, right? Just think about those of you that have totally shut down, because we're not going to have time to do too much more, right? You're all through high school, you're like, why do we need to know this? Why is this important? Who cares, right? This is an example of how we're taking our math and we're taking our science and we're like, hey, look at this. We can actually figure out how old something is based on that. Yes, sir.
So I is the square root of -1, which is a number that does not really exist, right?
All right.
I do not want to say that it does not really exist.
What is the practical real world application of I?
Some of it is beyond me. I will be totally honest. Benoit Mandelbrot did a lot of work with I. Basically, I is a number that was created because although we cannot take the square root of a -1, if you think about it, we do have situations where we have square roots of negative numbers. So how do we deal with that? So this is a number that gave us more of a concrete way of dealing with having to take the root of a negative number. Because the reality is it does occur in nature. So how do we handle it if it doesn't balance out like that? That's the best way I can explain it. Okay. Okay, so to determine the length of time since a plant or animal died, you measure the percent of carbon 14 remaining and apply the decay formula. Okay, so just look at this first example. What time is it? We have a little bit of time. Write the decay formula for carbon 14 using the value 100 as the initial amount present. Okay, so here's my formula, right? Okay. So using the initial amount of 100. So we're looking at 100 times 1/2, right? To the power of T over H. Right? So far, this formula looks just like my formula for exponential functions, doesn't it? Right, there's A, there's B, there's X. But if you look at my half-life formula, what else do I have in there? H. What's H going to be in this formula? What's the half-life of carbon-14? 5,730. 5,730 is the half-life.
Are they always going to give us the half-life?
Right now, yes. When we learn how to solve things, exponents using logarithms, no. Okay. Sometimes when we get to that point, you'll be asked to determine the half-life. Okay. So this, what I want you to understand, this is an exponential function, right? I just showed you that little graph using our silly little example, right? That's an exponential decay function. Half-life is an exponential decay function. Okay. Okay. Use the formula to calculate the percentage of carbon-14 remaining after 100 years. So here's my question here, right? Doesn't that word percentage kind of throw you? It's like, wait a minute. If I'm looking at this formula here, I'm thinking, what does N of T actually represent? N of T is the amount of the substance. It's the amount that's left. Just like when we have PERT, right? The amount equals P times E to the RT. A is the amount. N of T is the amount of substance. So why are they asking me for a percentage? How in the world do I do that? Who can give me a definition of percentage? Yeah, Cole.
Part divided by the whole.
Part divided by whole. Okay. Do you know any other definitions of it? So if I have $100 and I give you 25%, how much am I giving you? $25. If I have $100 and I give you 10%, how much am I giving you? Okay. Percentage is the amount of 100, the portion, the part of 100. That's what percentage is, the part of 100. So in this particular example, since they said we're starting with an initial value of 100, right? They said we're starting with an initial value of 100. When I figure out how much is left, it's actually a percentage because I'm basing it off of 100. Okay? So if I want to know how much is left after 1,000 years, N of T equals 100 times 1/2, 1,000 years over 5,730. Okay. Okay. So I get 88.61. Doesn't give me a unit. Probably grams, but it doesn't give me a unit. So if I start with 100 grams, in 1,000 years, I have 88.61 grams. What percentage do I have left? 88.61%, because that's what percent is based off of 100. Does this make sense? Okay. You need to have this formula memorized. This is our half-life formula. So you've got several formulas that I've given you. I guess next time we meet, I'll have to remember to go over those formulas with you. Okay, I'd like you to try to do numbers 3 and 4 by yourself on this worksheet. And then we'll pick up tomorrow with the other side of the worksheet. Okay? You do numbers 3 and 4 for homework. Yes.
On number 4, I got this times 10 to the negative 50.
Okay.
That's what percent is left.
I don't want to do the problem now because I want everyone to do it for homework, but we'll go over it. Let me see your actual formula here.
So I can't put in a grammar school, so I was.
Yeah, that's fine.
That's entirely possible.
Yes, sir.
I got an answer for the half-life.
To the